Welcome to today's lesson, Exponential and Logarithmic Models. There are a lot of applications for exponential growth and decay, and sometimes we have to use logarithms to solve these kinds of problems. So just keep in mind that our model for exponential growth and decay is y equals a sub 0 e to the kt, where a sub 0 is the initial amount, k is our growth or decay rate, and t is time. So when k is positive, we're going to be growing exponentially, and when k is negative, we're going to be decreasing exponentially. Example 1. What annual rate of interest compounded annually should you seek if you want to double your investment in 5 years? So let's say that we had an initial investment of 100. If we doubled it, we would get 200. It says we're compounding annually, so n is equal to 1. T is equal to 5 years, and we want to know what would R have to be for this to be true. So let's remember that A equals P times 1 plus R over N to the NT. I'll plug in 200 for A, 100 for P. I'll have 1 plus my unknown R divided by 1 times 1 times 5. Now if I divide both sides by 100 and do a little simplifying, I get 2 is equal to 1 plus R to the 5th power. Now you might think we'd need to use logarithms to solve this, but the fact is we don't have a variable in the exponent. So really all we have to do is we can raise both sides to the 1/5 power, because this will cancel. So basically we'll have 2 to the 1/5 is equal to 1 plus R. 2 to the 1/5 is equal to, from my calculator, 1.14869, which is equal to 1 plus R. And then if I subtract 1 from both sides, I get R is equal to 0.14869. Written as a percentage, the rate would have to be equal to 14.87%. Example 2, a colony of bacteria increases according to the law of uninhibited growth. If n is the number of cells at time t, write n as a function of t. So we're basically going with A equals a sub 0 e to the kt, but they're telling us to use n to represent our bacteria. So we can then say that n is equal to our initial number of bacteria, e to the kt, and if it's growing, k has to be positive. Part B, if the number doubles in 3 hours, find k. Alright, if the number doubles, let's just say that our initial value is 10, which means our final value would have to be 20, and we know that this is happening in 3 hours. So we'll say then that 20 is equal to 10, e to the k times 3. We'll divide both sides by 10, and we'll get 2 is equal to e to the 3k. Now we do have a variable in the exponent, and the only way to get rid of that is to use logs. And because this is a base e problem, I'm going to take the natural log of both sides, because the natural log of e cancels and the right side simplifies to 3k. We know that 3k has to equal the natural log of 2, so k is equal to the natural log of 2 divided by 3. And if we calculate this to 4 decimal places, we get that k is equal to 0.2310. Part C, how long will it take the colony to triple? So we know now that n is equal to our initial value, e to the 0.2310 t. If the colony is tripling and we say that our initial value is 10, then our final value is going to be 30. So we'll say 30 is equal to 10 e to the 0.2310 t. We'll divide both sides by 10, and we get 3 is equal to e to the 0.2310 t. Again, we're trying to isolate a variable that is in an exponent. To do this, we're going to take the natural log of both sides. So we get the natural log of 3 is equal to the natural log of e to the 0.310t, or the natural log of 3 is equal to 0.2310t, which means that t is equal to the natural log of 3 divided by 0.2310, and this is approximately equal to 4.8, and remember our unit of time in this problem is hours. Example 3, traces of burned wood contain about 1.67% of the original amount of carbon-14. If the half-life of carbon-14 is 5,700 years, about when was the tree cut and burned? So when we talk about half-life, we're talking about exponential decay. So we're still going to be using that A is equal to A sub 0 e to the kt, and know that half-life means how long does it take for something to decrease to half of its amount. So basically, if we start with A sub 0 equaling 10, half of 10 would be equal to 5, and we know that this is going to happen in 5,700 years. This is allow us to calculate our decay rate. So I'll plug in a 5 for A, a 10 for A sub 0, and then e to the k times 5,700. So now I'm going to have 1/2 is equal to e to the 5,700k. I'll take the natural log of both sides, and I get that the natural log of 1/2 is equal to 5,700k, or k is equal to the natural log of 1/2 divided by 5,700. Now this is a really small number, so I'm going to write it in scientific notation, and I get negative 1.21605 times 10 to the negative 4. So now that I know my k, I can say then that A is equal to my initial value, e to the negative 1.21605 times 10 to the negative 4 t. Now this is where it gets a little confusing. It says that the wood contains 1.67% of the original amount of carbon-14. So that means that A is equal to 0.0167 of the original amount. So I'm going to substitute this in for A. So I have 0.0167. A sub 0 is equal to A sub 0 e to the, I'm just going to write it as k for right now, e to the kt. We know that k is equal to that value. Notice how the A sub 0's cancel out. So now I've got 0.0167 is equal to e to the negative 1.21605 times 10 to the negative 4t. Anytime I have a variable in the exponent, I'm going to have to take the natural log of both sides. So I'm going to have the natural log of 0.0167 is equal to the natural log of the right side. That's going to cancel out with the e, so this will be equal to negative 1.21605 times 10 to the negative 4 times t, and finally t is going to be equal to the natural log of 0.0167 divided by negative 1.21605 times 10 to the negative 4. And this is equal to approximately 33,653, and we were measuring time in years. That's all for now. Thanks for watching.